All right, now the next thing I'd like to talk about is called the product rule. And it's a way of computing the probability of an intersection. So this is a way of computing the probability of an intersection. And this comes directly from the definition of conditional probability. Let's recall that the probability of E given F is the probability of E intersected with F divided by the probability with F, of F. If we multiply both sides by P of F, we end up with the following. Let me write PE intersect F first is equal to the probability of E given F times the probability of F. Okay, so this is the product rule. Let me highlight it. I'm going to highlight it in green here. This is the product rule. There we go. Product rule is that right there. So take it, frame it, put it up on your fridge. Don't forget it. It's important. So the probability that both E and F happens is the probability that E happens, assuming that F happens, times the probability that F happens. So it's the percent of the time that E happens when F happens times the percent of the time that F happens. I think that's kind of intuitive. Now this is one reason why we require that we have probabilities be numbers between 0 and 1. If we had them be percents, then this rule simply would not work out. Okay. The definition of conditional probability also would not work out if we used percents. Anyways, let's look at some examples of this. Here is a simple example. So 5% of Americans commute to work, and here I mean American workers, so Americans commute to work using mass transit. Trains, buses, whatever. And of these, 40% commute primarily by train. So that's, the subway, or, it could be, an Amtrak train or a train, the trains that run from New Jersey or Connecticut or, further up in New York down to New York, whatever. All sorts of different kinds of trains. And, yeah. So the question then is, what percent of all Americans commute by train? So let's consider the two events. Let's let T be the event that somebody travels by train. Let's let M be that somebody travels by mass transit. Okay. So what we would like to find out is the probability that somebody travels by train, period. And I would like to note that if you commute by train, that the T intersect M is just equal to T, because those commuting by train is a subset of those commuting by mass transit. So the probability that a random American travels by train is the same as the probability that they travel by train and by mass transit, which is the probability that they travel by train given that they travel by mass transit times the probability that they travel by mass transit. Now, the probability that they travel by train, given that they travel by mass transit, is 0.4, and the probability that they travel by mass transit is 0.05. So this works out to 0.02. What this means is that 2% of Americans commute to work primarily by train. And presumably you are in that 2%. I am. I take the train to work. Okay. Now, we're often going to be using the product rule in really sort of more sort of complicated scenarios. In fact, let me do something that we've done before, but use conditional probabilities and some different techniques to compute it. So again, a sock drawer kind of example. I've got 6 white and I've got 4 black socks in my drawer, and I'm going to pull out 2. And the question is, what is the probability I get a matching pair? Well, the way we would have done this before is to count the number of ways that I could get a pair of white socks, the number of ways I could get a pair of black socks, divided by the total number of ways that I could get a pair of socks. But let's do something a little bit different this time. Let's draw a tree diagram that represents all the sequences of what I could choose. So my first choice could be a white sock or a black sock, and after I choose that first white sock, I could choose another white sock or a black sock, or if I choose the black sock first, I could choose a white sock or another black sock. Now above each of these, I'm going to write the probabilities that each of these things happen. Now the probability that I choose a white sox, well, there's 6 out of 10 total, so my probability of choosing a white sock is 6 out of 10. Whereas my probability of choosing a black sock is 4 out of 10. Now over here, in these second set of branches, I'm going to write the conditional probabilities. Assuming that I've picked a white sock, what is the probability that I choose another white sock? Well, there are 5 white socks left, and there are 9 white socks, or there are 9 socks altogether, so the probability I choose a white sock is 5/9. The probability I choose a black sock is, well, there's still 4 in the drawer, and there are 9 total socks left, so it's 4/9. As far as if I choose a black sock first, if I choose a black sock, the probability of I choose a white sock is, there's 6 white socks left, so 6 out of 9. And the probability I choose another black sock is, there are 3 black socks left, and that's out of 9 socks total. So let's notice that, for example, let's just look at this first branch. The first branch is just a regular old probability, the probability that the first is white. But the second branch is a conditional probability, so the probability that the second is white given that the first is white. Okay. Now the product rule says that if I multiply these conditional probabilities, I get, well, it says if I take, for example, excuse me, the first sock, I've got a 6 out of 10 chance of drawing a white sock, and then a 5 out of 9 chance of drawing a second white sock. So the probability of drawing 2 white socks is, by the product rule, the product of these two guys, which is 6 tenths times 5/9, which is equal to what? I guess 1/3. The probability of drawing a white sock than a black sock, this was 4/9. It's going to be 6 tenths times 4/9, which is equal to, whatever. We only care about a matched pair, so I'm not going to write this out. the probability I draw a black and then a white, drawing a black is 4/10, drawing a white after that is 6/9, whereas drawing a black after that is 3/9. So the probability of drawing a black and then a white is 4/10 times 6/9, which is, whatever. And the probability of drawing two blacks in a row is going to be 4/10 times 3/9. I care about this because I'm concerned with drawing a pair. And this is equal to what? I guess this is equal to 2/15. 1/3 times 2/5, yeah, 2/15. Great. So that means that the probability of getting a matching pair is the probability of getting two white socks plus the probability of getting two black socks, which is 1/3 plus 2/15, and that's 5/15 plus 2/15, which is 7/15. So just under half the time I'm going to get a matching pair if I just draw out two socks. I should draw out three socks. If I do, I'm guaranteed to get a pair. Think about that for a second. So this tree diagram that I just drew is called a probability tree. So a probability tree is a tree diagram which we've discussed in the previous chapter with probabilities drawn or written on each branch, so on the branches. Now here's how we set up a tree diagram, or excuse me, a probability tree. The first thing, so to set up a probability tree, first, it'll be a 1, we draw a tree diagram that represents the sequence of all sequences of outcomes that can happen. And let me sort of represent that up here. It could just keep going, whatever. A, B, C, D, E, F, G, H, I, J, whatever. Second, we write probabilities on top of the branches. And what are these probabilities? So the probabilities on the first set of branches are just the probabilities of those events. But the probabilities on the next set of branches are the probability of that event given all preceding events. So this gets the probability of C given A. This gets the probability of D given A. This gets the probability of E given B. This gives the probability of F given B. So it's really, these are all really just conditional probabilities that, this event happens, assuming everything prior to it happens. So, again, let me just write that out. So, this is the probability that the event on the right happens, assuming everything to the left happened. Okay. And then 3, if we multiply all of the numbers along, one branch, one possible sequence of outcomes, we get the probability of this sequence of outcomes. And this basically follows from the product rule again. Okay. So we just did an example of that, but let's do another example of this. Let's say a little bit more complicated example that I just came up with. So this is the 2012 presidential election. Now, Quinnipiac University in Connecticut does a lot of polling, and their data right now says the following. Of the three main Republican candidates who are, so the Republican candidates right now, the top three are Newt Gingrich, and if I were you, I wouldn't go by, if I were Newt Gingrich, I wouldn't go by Newt. I mean, that's kind of a bad nickname, but whatever, it's him. Mitt Romney, again, I don't know if that's even a nickname, but that's just an awful name, Mitt. And the third is Herman Cain. Herman Cain is still in the top three. I mean, that's absurd. Come on, people. I mean, we've already seen that Herman Cain is completely unfit to be the president of the United States, So I don't know why he's still in the top three. Ubeki, Becky, Stan, whatever. Um, you know, it's absurd that people still want to vote for him. I think they're just being contrary. But anyways, but they've released the following data. So the probability that Gingrich will be the nominee is right now it's 42%. The probability that it's going to be Romney is 35%, while the probability that it's going to be Cain, assuming that's one of these three guys, is 23%. So this is what the polls say right now. At least, assuming people prefer this right now, this is who they're going to vote for. Hint, it's going to be Romney. It's clearly going to be Romney. He's been in second place the whole time. Everybody's been going up and down like yo-yos. Romney's the only constant. He's the moderate one. He's going to be the Republican candidate. Everybody, just get over all these other candidates. I'm not even saying I like Romney. It's just what it is. Mark my words. Anyways. Now, what is the probability that each of these candidates has of winning over Obama? So, win over Obama. Here's why it's going to be Mitt Romney. The probability that Gingrich wins over Obama is 45%. The probability that Mitt Romney wins over Obama is 50%. It's pretty much a dead heat right now. Actually, Obama has a slight edge, but it was so small that I decided to say it was 50%. And Cain, 43%. I don't even know why anybody would vote for Cain over Obama. If people think that Obama's foreign policy is bad, I mean, just listen to Cain. Just listen to anything he says. Come on, people. But Romney is the most likely to win. He's moderate. He's going to be their nominee. Okay. Now let's construct a tree diagram here to answer the question, what is the probability of Obama winning? So our tree diagram, first we've got three choices which are that Newt Gingrich gets the nomination, that Mitt Romney gets the nomination, or that Herman Cain gets the nomination. And above these, we write the probability that they get the nomination. Gingrich gets 0.42, Romney gets 0.35, I mean really it's 1, but whatever, and Cain gets 0.23. And now above this, we'll write whether Obama wins or Gingrich wins, or whether Obama wins or Romney wins, or whether Obama wins or Cain wins. Now, Obama against Gingrich has a 55% chance of winning and a 45% chance of losing. Over Romney, he will win half the time and will lose half the time. And against Kane, he will win 57% of the time and he will lose 43% of the time. Now what we're going to do is we're going to follow all branches that lead to Obama winning. So that means that the three branches we're going to look at are this branch right here. We're interested in Obama winning. So Gingrich and then Gingrich getting the nomination and then Obama winning. Romney getting the nomination and then Obama winning, or Kane getting the nomination, come on people, and then Obama winning. So the probabilities that we care about are here the straightforward probabilities, the probabilities of each of these guys, and these probabilities here are conditional. 0.55 is the probability that Obama wins given that Gingrich is the nominee. 0.5 is the probability that Obama wins given that Romney is the nominee. 0.57 is the probability that Obama wins given that Kane is the nominee. So I can figure out the probability of each of these things, the probability of Obama winning and Gingrich being the nominee, by multiplying along here. So let me just, we're going to follow all the branches leading to Obama winning, and then we're going to add them up. So let me just erase this here so that I can write all of these numbers. So the probability that Gingrich is the nominee and Obama wins is 0.42 times 0.55. The probability that Romney runs and Obama wins is 0.35 times 0.5, and the probability that Kane wins, or no, Kane gets the nomination but Obama wins is 0.23 times 0.57. Now, I didn't compute these numbers beforehand, so just give me a second to do that. 0.42 times 0.55 is 0.23. 0.35 times 0.5 is 0.175, and 0.23 times 0.57 is 0.1311. So let me write those numbers down for your edification. So these numbers work out to be 0.231, 0.175, and 0.1311. So 23% of the time we expect Gingrich to run and Obama to win. 17.5% of the time we expect Romney to run and Obama to win. And 13% of the time we expect Kane to run and Obama to win. We add these numbers all together, and what we get then is 0.5371. That adds up to 0.5371. So there's a almost 54% chance of Obama winning according to these polls. All right. Let me just, we're going to be doing a couple more tree diagrams in the next couple of sections, so let's leave it at that.